Fusion Mobile, quality e-learning experience on the go.
Mobile e-learning clinic. My name is Sonia Olaoluwa, and I've been taking you through the physics course. We'll be talking about equilibrium of forces. In this topic, we'll look at the concept of equilibrium. We'll talk about moment of a force. We'll look at couples. Then we'll talk about equilibrium under parallel forces. We'll talk about center of gravity, triangle of forces, conditions for equilibrium of non-parallel forces. And we'll also look at stability of a body, and that's where we'll consider the types of equilibrium. We'll talk about density and upthrust. We'll look at Archimedes Principle and flotation, the application of Archimedes Principle, and we'll talk about the hydrometer. The concept of equilibrium. Well, when we talk about equilibrium, what always comes to mind is balance. Everything summing up. So many forces can be acting on a particular point, and the forces can't get the thing to make any kind of movement. This is because there is an equilibrium. All the forces cancel each other out. And when we talk about moment of a force, the moment of the force is a turning effect a force has on an object. It's a turning effect a force has on an object. Moment of a force is measured as the force, that's moment, is measured as the force multiplied by the distance in direction of the force. The force multiplied by the distance in direction of the force. Now, on several occasions, the direction must always be perpendicular to the force. It must be perpendicular to the force when you measure the direction on the distance. So, in moments, we'll take more time to talk about moments in details. Now, for when you want to open your tap, you use your two fingers and you turn the tap. Yes, you apply some force. There's a force that is applied because it's force that is bringing about a turning effect, and the turning effect is rotational. It is called the couple. Now, this couple is you having two forces acting the same amount of force. You are having two equal forces acting on two different sides, in fact, two opposite sides of a particular device. When such thing happens, we call that type of force a couple. In a short while, a question will pop up on your screen. We'd like to see what your response will be to it, so we can understand, we can know what you understand or what you understood from what has been taught so far. Equilibrium under parallel forces. When we talk about parallel forces, what do we mean? We mean forces that act in either the same line of action or opposite line of action. That is, they are parallel to each other. When we say two lines are parallel, it means they act kind of in direction whereby those lines cannot coincide, they cannot meet, they do not have a joining place. So when we talk about moments, we see that coming to pass, we see that coming to play in moments. You see two children sit on the seesaw and one goes down, the other come up. If both of them are of the same mass and they are sitting at the same distance from each other, the seesaw stays stable unless one of them applies an extra force to make it begin to swing. Now, when we talk about moments, for equilibrium to occur in any system of forces, for equilibrium to occur, there must be the summation of all the forces acting on that particular system must be equal to 0. So, in terms of parallel forces now, it means maybe we are having all our forces are along the y-axis. All our forces are along the y-axis. So we could have upward forces and downward forces. So when we sum our upward forces, the summation of upward forces should give us the same thing as that of our downward forces. Summation of force upwards should be the same thing as summation of force downwards. And also, another thing to take note of when we're working with moments is, apart from the fact that upward forces must always be equal to downward forces, also summation of forces on your left hand side should also be equal to summation of forces on the right hand side. Summation of forces that swing in your left hand side direction should also be equal to the summation of forces that swing in your right hand side direction. We said moment is all about turning effects. So let's take, for example, we have this particular system. We have a force acting here. We have another force acting here. We have a force there. We have another force here. This is F1, F2, F3, F4. Or let me use arrows instead of drawing boxes. Considering this, our upward forces are F2 and F3, so we'll say F2 plus F4 should be equal to F1 plus F3 based on this. In like manner, F1 swing to the left, it swings from right and it swings this way, and that's anti-clockwise. Okay, I think I should have used anti-clockwise and clockwise, so let me change it now. Let me say anti-clockwise and anti-clockwise and clockwise. So F1 swings anti-clockwise, F4 also swings anti-clockwise, F2 swings clockwise, F3 swings clockwise. So F1 plus F4 should also give us F2 plus F3. All these conditions, both of these conditions must be met for there to be a balance, for there to be an equilibrium under parallel forces. Alright, let's try out this question. It's a question on moments. We have this system of forces acting on a beam. The beam is said to be weightless and without any, it does not have its own weight. So we have this here, and this is the system. For us to calculate, I remember I told us earlier that moment equals to force multiplied by perpendicular distance from where the force is acting. So here we can pick our first force, and I said also we should consider clockwise and anti-clockwise. For our left hand side we have our anti-clockwise moments here, so I'll start from anti-clockwise. The first one I have is my 5 multiplied by 3 plus, we are looking for x. We're trying to find the distance where we'll place this 20 such that there will be an equilibrium, that the swing will not move to one side. Then we'll take our next one, which is 10 multiplied by 2 should give us 20 multiplied by x. Why did I say should give us 20 multiplied by x? 20 is on the other side of the expression, and it is coming on the clockwise, in the clockwise direction. So when we multiply what we have here out, we have 15 plus 20 equals to 20x. We have 20x equals to 35. Our x will be equals to 35 divided by 20, which is equals to 1.75 meters. So for this system to be balanced, our 20 Newton weight must be placed on the 1.75 meter mark. That's when the entire system will simply remain as it ought to be at equilibrium. Center of gravity. Many times we do say the center of gravity of a matter, that is the area of concentration or the area of importance. Well, the center of gravity is a very interesting point in everything, in every matter. It is the place where the weight of a thing is most concentrated. It is the region where the weight of a thing is most concentrated. It is usually found in the center of regular objects. It's usually found in the center of regular objects. There are two ways in which you can go about trying to detect the center of gravity of objects. One way is easier to use, can be used for any, whether it is a regular object or not. The other way can only be used with regular objects. Let's start with one for regular objects. But just take the object, maybe if it is a meter rule or something, place it, get a pivot or something that has a knife edge shape, that is something with a shape like this. Then place the object on it and keep adjusting it until it balances in such a way that it does not swing to either side. When it balances and it doesn't swing to either side, mark that particular position that is on top of the knife edge. That is your center of gravity. The second method that can be used is by creating holes, say about 3 to 5 holes on the object, or marking the object about on 3 to 5 different locations. Now, that can be used for both regular and irregular objects. Let's say I have this irregular shaped object. I can create my holes here, 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 and here. But it is good to have them on different positions around the shape, the object. That would help to detect more accurately. Now, you pick after creating these holes, you take a plumb line. That is a line. You can take a rope and attach something to it, and you put it through the hole. You fasten it and you hold it up. The object would automatically adjust by itself. Now, with your pencil or a chalk, you can draw a straight line on the plumb line, and you pick another hole and you repeat the same process until you have repeated the process for all of the holes. The center of gravity would be that point where all the lines coincide. While conducting this experiment, you could have something like this. You could have something like the center of gravity will be where all the lines coincide. That place where all the lines meet. That would be your center of gravity. When you're using the knife edge, this is your center of gravity. And when you're using the plumb line, this is your center of gravity. Whichever method you choose to use, you would get it. For you not to have too much difficulties, especially when working with irregular shaped objects, you can use maybe 2 to 3 different lines. The more the lines that you use, the more accurate you would be in your solution, in your that your center of gravity would be. Triangle of forces. The other time we were talking about vectors, I made mention of the parallelogram theorem. Well, the triangle of forces theorem is identical to the parallelogram theorem. It simply shows us a structure, a way in which you can actually try to put things together and resolve forces. We can have we can have 2 different forces acting to balance out one force. And that's where we find triangle of forces come to play. The other time I said resultant and equilibrant are equal, but they are always moving in opposite direction. For example, you could have two forces acting at angles from each other, and the third force, maybe the weight, pulling through the center. Force and a force. This is F1 and this is F2. Then you have a weight going down the center. Now this kind of creates something like a triangle of forces. Of course, just like the to draw this triangle, what we need to do is to identify and connect all the forces one to the other, and then it will give us what we want to see. Triangle of forces theorem says that when you draw the forces acting, connecting them end to end, the third line that would come up would be the resultant of the forces, or the equilibrant of the forces. So, like in this case, I can start with my F2 by drawing my F2 the way it is. We're told always to represent our... After drawing my F2, I can also draw my F1. My F1 goes in. This is my F1. This is F1 and this is F2. Now my resultant would be my equilibrant, the one that will cancel out the effect of these two, would be my W. So that is what this particular theorem. I arrange the forces. When I arrange them, if I should draw them to scale, my resultant or my equilibrant is the one that will point downward. My resultant will point from the beginning back to the ending. That will be the resultant. But my equilibrant will balance it out. So that is what that law of triangle of forces has to explain. Other things we should know about equilibrium in bodies is that when you are balancing, I said it earlier, remember that you have to consider upward and downward forces. Also, you have to keep at heart that some objects might be very long, which will give even more space for us to balance out certain things. Some objects also might have their own individual weights. Some objects might have their own individual weight. Like a ruler can have a weight, and the weight of the ruler can offset the balance. And some objects, their weight varies based on the thickness of the object. For example, your cooking spoon. The weight of the cooking spoon at the edge, where the place you use to stir your soup, the place that goes into the pot, is higher than the weight where you hold it at the handle, because that region has the largest volume compared to this region. So even on its own, when you place it on the knife edge in the middle, it already bends towards one side. So all these things need to be put into consideration when we are trying to balance out in moments and balance out forces generally, putting forces in equilibrium. Yes, let's look at conditions for equilibrium. We've talked about some of them, especially equilibrium for forces that are under parallel, for parallel forces. We mentioned the effect of coplanar forces, that is upward and downward forces, and we also considered the forces due to the moments. Of course, apart from coplanar forces and that, when it comes to non-parallel forces, there are about 3 of them that also we need to put into consideration. Start with the coplanar forces, of course, very, very important. Apart from the coplanar forces, we also have to consider the total forces acting on the body or at that particular point. we have to consider all of the forces acting on the body on that particular point. And as well, we have to consider the moments about that particular point. Sometimes moments can actually help us to sort out some of the issues that we may come up with. But let's take a question, maybe to shed more light on, I believe a question should shed more light on what we've just talked about. Alright, let's take this question, let's look at this particular question. We're being told that this weight up here is 1 kilogram, and its weight is what is acting downward. Energy is acting downward this particular way. That means our weight is acting this particular way. But if we look at the entire thing, we are asked to find out what is the force that will be used to pull this thing, that it will be able to climb the slope edge. So that's what we want to find out. We also know that m equals this. We also know that our g will always be equal to 10 meters per second squared. So how do we go about it? I would recommend, for good visibility, you might decide to redraw the diagram, taking out the slant, and they already give us y-axis and x-axis. So why not make your y-axis and your x-axis look the way they ought to look, and identify what is not looking the way it ought to look. If this is our y-axis, it means we should have something like this here, and the angle here will be equal to the angle here, using alternate principle of alternate angles from mathematics. So this place should be 30 degrees. So if we should be redrawing that, when we redraw that, we would have something looking like this. We have this acting upward. That's the normal reaction. Of course, this is our y-axis, and this is our x-axis. Then the pulling force P would be there. Now note this, we'll have our y-axis continue downward. Then we'll have this one that is looking like this will now look something like this here, and we'll have this place to be 30 degrees. We'll have that place to be 30 degrees. And we know that at this 30 degrees point, we're already having mg. So everything we want to calculate centers on mg. Now, let us resolve our mg to upward and downward forces. It will make work easier for us. Because our angle given is not connected to our horizontal, we cannot use the law that we used to use. So I always like to work with horizontals. So I would calculate what this is, and this will be 90 minus 30, which will be 60 degrees. Now, using this 60 degrees, I can now take my vertical to be sine and my horizontal to be cosine. So, resolving this particular one into my horizontal and vertical forces, of course, it is acting in opposition to both of them. It's pointing this direction. So, resulting this one into vertical and horizontal, I'll start with horizontal because the first question was find P, and second question was find R. On the x-axis, I'm resolving this. I'll have this particular expression will be mg. Sorry. The expression for the x-axis would be this is moving in a positive direction, that is P, and this is going to be coming in the negative direction, minus x-axis, that means cos, that's mg cos 30. I'm sorry, cos 60. I'm not working with this anymore. I'm working with my 60. mg cos 60 degrees should be equal to 0, because for the body to be at equilibrium, it means the sum of everything on that side, on that particular axis, will be equal to 0. The sum of all coplanar forces must be equal to 0. So, for this to be equal to 0, my P then will be equal to mg cos 60. I know my m to be 1 and I know my g to be 10, and cos 60 is 0.5. So, when I multiply it all together, I have my answer as 5 newtons. When I consider also my y-axis, for my y-axis, that's vertical axis, I'll have r, of course this one is pointing downward again, minus, that's mg. For vertical, I always work with sine 60 degrees should be equal to 0. Why I'm having 0 immediately is because there are no other forces acting in that region. This is the only one acting horizontally, and this is the only one acting vertically, apart from this one that is acting slant. There are only 3 forces there, and this does not have a vertical component, this does not have an horizontal component. So my r then becomes mg sine 60 degrees, which is 1 times 10 multiplied by 0.866. When we use your calculator to calculate this, we'll have 8.66 newtons. A body is said to be stable when, if displaced slightly, it returns to its original position. That is, you have a particular object, you push it, not like you push it very, very hard as to throw it away, but you push it away from its original position and it sits back into its position. It means that in that original position from which you moved it, from which you adjusted it, sort of, it is stable. Your chair is stable on 4 feet. That is, when all the 4 feet of a seat is there, it is stable. And if you displace it a bit, it would always come back to that position. The center of gravity is one of those factors responsible for the stability of objects. A body is said to be unstable if, when displaced, it loses its stability completely and moves some distance to find stability once again. Just displaced slightly, it makes a lot of motion before it can get stability once again. And the body is said to be it's said to possess a neutral stability, or it's said to be at neutral equilibrium if, when slightly displaced, it loses its previous stability but finds another stability quickly within a very short distance. In its new position, it finds another stability. So let's take, for example, a triangle seated like this. When you push it forward, so long as you've not pushed it up to like half of the entire thing lifting, it will fall back to its original position. Now, this is how a body that is stable looks. Its center of gravity is low within the object. Now, when you push it maybe up to something like, that's too much. When you push it from this angle and you push it even up to something as slant as this, if you take your hand off, it falls back to its original position due to its low center of gravity. The low center of gravity makes it want to stay. That low center of gravity still puts it back to where it's coming from. It still pulls it back to where it's coming from. But this is in a stable equilibrium. An unstable equilibrium is something like this. You find a way to balance the object. Of course, we all know it's possible to balance the object somehow. Maybe holding it for a while until it is stable. Then you just give it a small push from there. And next thing you notice is it falls down completely. It loses its balance completely. That's the center of gravity. This is the unstable equilibrium. In a neutral equilibrium, you push the object, it changes its position, but it maintains its stability. It maintains its stability, unlike the unstable position whereby it loses stability completely and picks a totally different posture. It maintains the stability, yes, maybe a bit different, but where it was on the floor before may no longer be on the floor, but the stability is very much retained. Its stability remains the same because the center of gravity is situated in the center of the object. So it is like having the center of gravity at the same point at every time. So those are the three types of equilibrium that we have: the stable equilibrium, the unstable equilibrium, and the neutral equilibrium. Equilibrium in liquid bodies. I remember telling us some time ago that when the weight of a thing is calculated or a person is measured while the person is on the ground, and when the person's weight is also measured when the person is immersed in water, the weight of the person changes. Yes, the weight of the person changes due to some forces that act on that body while the body is immersed in the water. Equilibrium in liquid bodies try to look at in ways in which the forces acting on solids when immersed in water or when liquids also exert their own force, how they all balance out. Because of the equilibrium that exists in liquid bodies, that's the reason why we can have things that float and certain things sink. Every one of them try to find a kind of balance, a kind of equilibrium. The knowledge of this equilibrium in liquid bodies also is one of those things that is used in the design of machinery, heavy machinery such as submarines, which can sink in the seas and come to the top of the sea once in a while when it is required to do so. One of the major principles which is applied when it comes to equilibrium in liquid bodies is the Archimedes Principle, density and upthrust. So when it comes to density, what do we mean? And when it comes to upthrust, what do we mean? Let me start from upthrust. Upthrust is the force which a fluid Upthrust is the force which a fluid uses to push against substances that try to come into it. And the upthrust of a body is very much dependent on the density which the body itself has. That is the fluid, the liquid. Density applies to both solids, liquids, and gases, but upthrust is very, very peculiar to fluids, liquids, and gases. Now, when the upthrust is bigger when the liquid or the gas is denser. It has a stronger force when it is thicker, it is more concentrated. And density has the formula which is mass divided by volume. that is mass per volume. It is the ratio of mass of a substance in a particular volume. So it's kind of like creates a kind of pressure, and that kind of pressure is what is described as upthrust. Even though upthrust is a force, but the upthrust this is what keeps substances that afloat in the liquid or in the gas. That's the reason why when we fly an helium balloon in the normal atmospheric air, the helium balloon tends to fly higher than your normal air balloons. And why does your helium balloon float higher? Because the helium gas is actually lighter than air. It has a density which is smaller than that of air. So that density takes it higher, while the denser things, which are heavier things, come underneath it and keep pushing it up, using their upthrust to propel it to a higher point. Okay, density, relative density. So, how do we calculate density? For solids, we can go ahead and calculate density directly. Density is mass divided by volume. But when it comes to fluids, we cannot calculate density directly. So we'll go about calculating what we call relative density. Yes, you can actually calculate the density of a fluid directly by measuring what quantity of that fluid, that is, what volume of the fluid, and what is the weight. But oftentimes it does not oftentimes it does not meet our needs. We need to understand the relationship between densities of different components, especially different fluids with water. So, how do we calculate the relative density of other liquids? Let's say I want to calculate the relative density of alcohol. Relative density of other liquids is always calculated in relationship with that. Relative density of fluids is always calculated in relation to that of water. So we should note that what you want to know is relative density, RD. It is always the density of the liquid or fluid divided by the density of water. And it can also be the mass of fluid divided by the mass of equal volume of water. So you can measure 25 liters of this fluid, and you can measure 25 liters of water, and then you check the mass of 25 liters of that fluid. I do. I know. I'm just using it as an example for them. They think at least something they can imagine. You can measure 5 liters of this fluid and measure 5 liters of water, then find out their mass or check their weights. It can also be weight of liquid divided by weight of water. If you take note of all the formulas I've given, whatever you are using to divide for the other, for one, must be the same thing you're using to divide for the other. If you are using mass for the liquid, then you use mass for water. If you are using density for the liquid, you use density for water. If you are using weights for the liquid, you use weights for water. And when you're using mass or weight, you make sure that it is equal volume. I also like you to bear in mind that there is also a relative density bottle which you can use to take your measurements, and it will make things much easier for you. This is when you want to do the direct method. Archimedes Principle. Archimedes Principle is a principle that was propounded to solve problems having to do with flotation and sinking of objects in liquids. Now, the principle states that when a body is wholly or partly immersed in water or in a liquid, it displaces the volume of water which is equal to the mass it loses. In other words, it loses its own weight and it displaces a volume of water. That is, let's say you have a stone tied to a scale and you put that stone in water. A specific volume of water would be taken out or will be moved because of the presence of the volume of the stone. My weighing balance will be showing a particular reading initially before I put the stone in the water. Now, when the stone goes inside the water, when my stone goes inside the water, the stone loses its weight, loses some of its weight, and some of the water is spilled into the vessel. Now, the weight of the water in this vessel will be equal to the weight loss of the stone. That is what Archimedes Principle states. So, yes, the stone is heavier than water and is asked to take its place inside the water, but it has to lose something to augment for what it sent out. Now, it is this principle that, the understanding of this principle, that has helped in the development of very many machinery that is being used today, especially ships. Especially ships. We have different kinds of ships, both your aircrafts, your submarines, your cargo ship, your tourism ship, even your flying boats, your canoe. All of them work with the understanding of this principle. This principle is one of the major things that makes many of these devices that we put on the water today stay afloat. Yes, upthrust is there. It is one of the principles that explains the function and the power of upthrust. Now, these are some of the many applications in which where we find Archimedes' principle being put to use. Let's take this question. An object of mass 60 grams and density 10 gram per cm cube is suspended by a thread and lowered half of its volume in a liquid of density 0.8 grams per cm cube. What is the tension on the thread? Very interesting. The tension on the thread. We're told the mass of the object, so we know that mass equals 60 grams. That's mass of the object. We also know the density of the object to be 10 gram per cm cube. We also know the density of the liquid to be 0.8 grams per cm cube. So what we're looking for now is tension on the thread. The first thing we can calculate out of here is what is the volume of the mass that was immersed. So to calculate our volume, we know rho equals to m over v, thus v will be equal to m over rho. That will give us 60 over 10, which will give us 6 cm cube. If the volume of the object now is 6 cm cube, and we're told that half of it was lowered into the water, which means the object will definitely displace half of 6 cm cube of water, of the liquid rather. So we can say volume displaced, that is volume of liquid displaced, would then be equal to 6 divided by 2, which is 3 cm cube. And we can now calculate the mass of liquid displaced. The mass of liquid displaced would now be the density of liquid multiplied by the volume of liquid displaced, which will give us 0.8 multiplied by 3, which will give us 2.4 grams. That will give us 2.4 grams. So the weight that will be lost by the object is 2.4 grams. So what will be the new weight of the object, the new mass of the object? Object new mass, Mn, will be equal to original mass of object minus mass of liquid displaced. My new mass would then be equal to 60, which is the original mass of the thing, minus 2.4. So when we subtract, we'll have 57.6 grams. Now this 57.6 grams need to be converted to kilograms. So when we convert it to kg, we'll have it as 0.0576 kg. And of course, our tension is a force. So force is always equal to MA or mg in this case, which would be 0.0576 multiplied by 10, and that would give us 0.576 newtons. So that's the amount of tension that would be on the thread. The hydrometer is a tool that is used to measure the density of liquids. It has a bulb and a graduated body. Right now on your screen, you'll be looking at the image of an hydrometer. In the bulb of the hydrometer is the weight of lead, and the scale is on the body. To measure the density of the particular fluid, all you need to just do is look on the body of the hydrometer. It comes in different shapes and sizes. In this topic, we spoke about equilibrium of forces. We looked at the concept of equilibrium, that is balance. We talked about moment of a force, which is force in motion. We talked about couples, that is tugs and couples, when you are applying the same amount of force in opposite direction on two sides of a body, of a thing, causing a turning effect. We also talked about equilibrium under parallel forces, where we spoke more in detail on moments about a point. We looked at center of gravity, and we looked at the part of as things concentrate their weight on that center of gravity, and the application of the study of center of gravity. We also looked at triangle of forces, the principle of triangle of forces, that is two forces acting together. When the two forces acting together are drawn to form a kind of triangle. When two forces acting together are drawn with their head connected, with one's head connected to the other's tail, the line that will join the two of them together to form the triangle is the resultant or the equilibrant. We also spoke about the conditions for equilibrium. So conditions like as the coplanar forces must be equal to 0. The turning moments also must be equal to 0. These are for parallel, and for non-parallel, coplanar forces must be equal to 0. Turning forces must be equal to 0, and all the forces acting on it must be equal to 0 for that body to be at equilibrium. We also spoke about stability of bodies, where we talked about three types of stability. We talked about 3 types of equilibrium. We talked about the stable equilibrium. We talked about the unstable equilibrium and the neutral equilibrium. We spoke of density and upthrusts, their effects, and in relation with the Archimedes Principle. The Archimedes Principle states that when a body is partly or wholly immersed in a liquid, it displaces a volume of water equal to the mass it loses. So, which equal to the weight, rather, that it loses. It loses its weight. And this weight which it loses is also described as the upthrust of the liquid acting on the body. So the application of Archimedes Principle is seen in our ships, the boats, the aircrafts, balloons, and many other inventions that are being used today. We spoke of hydrometer as a tool which is used for checking and measuring the density of liquids. In a few seconds, some questions will pop up on your screen. Please attempt them, and if there is any part of the lesson which you do not understand, you can go over the lesson again. Thank you.